Thank you. Well, first of all, I want to thank Hilbert and Christoph for the kind invitation, but I also really want to thank the two of you for all the effort that you put into making this a very lovely program. I know it's a huge effort, and I'm sure you can think of much more pleasurable things to be doing, but we're all benefiting from this. I mean, I see not just us, but I see there's a lot of photos on the wall. So so thank you very much. Your efforts are appreciated, especially for the young people. I think it's been very good. So anyway, so let me begin. I was asked very recently a question from Alberto Ruiz and Juan Antonio Bartolo. So they were interested in a question about the classical Hardy-Littlewood maximal function and how it behaves when you take averages of it along lines. Okay, so this is a question that came about from their work that they've been doing for many years on the Helmholtz equation, and in particular weighted inequalities for the Helmholtz equation, and this is related to weighted Sobolev inequalities, and all of this dates back to a very famous paper of Koenig, Ruiz, and Sog on uniform Sobolev inequalities. This paper seems to is living a second life now. I've been to a number of conferences in the last few weeks, and there's been many talks on variants of this paper of Koenig, Ruiz, and Sog. So the question, so what Alberto and Juan Antonio were interested in, they were interested in a certain class of weights. So these are weights that satisfy the so-called the radial Misuhata-Takeuchi condition. So this is a weight that satisfies this condition. Is what you do is you look at the radial majorant of this weight, and then you compute the X-ray transform, and you require that to be bounded. So you can express this nicely in terms of some norm of the weight to be finite, and not these days, I guess this norm goes by the name of the triple norm. So what Alberto and Juan Antonio wanted to know is does the classical Hardy-Littlewood maximal function behave well with respect to this triple norm? Is it bounded? Okay. So they had some reasons to believe that it was the case. They knew of several consequences that were true and many other consequences that they would like to have been true. But it turns out to be not the case. Okay. So it's unbounded. The computation is not particularly difficult, but you have to do a little bit more than test the inequality on a characteristic function of a small ball. You have to take a sum of characteristic functions of small balls that are strategically placed. So this is a, well, it's this I won't write down, but it's a triple norm inequality, and you're just asking with respect to this norm, that is the Hardy-Littlewood maximal function bounded on this norm. So this is but anyway, that was just it just started to make, it just reminded me of another family of problems, which is what I want to talk about. And they have the same sort of flavor, but instead of taking a classical maximal function and looking at its averages over straight lines, you build the maximal function by taking a function and looking at averages over straight lines. And so there's kind of a large variety of problems that can be cast in this way. We've already heard a very beautiful talk from Malavika. She was talking about a certain aspect of this. But there are other problems, and I thought it might be a good time to revisit these problems. There are a lot of what I still think are quite interesting open problems, unsolved problems. And so I just want to use this hour and tell you, look at a few of these questions, tell you a little bit about what we know, and tell you what we don't know. Okay, so I'm going to begin by looking at these maximal functions. So this is going to be defined with respect to a line configuration. So I'm going to take a bunch of lines. Whoops. Okay, so these are going to be, these are in some Euclidean space. So for me, these are lines mean finite line segments. But they can be quite general. They could have any position, different lengths, different directions. They could be finitely many of them. There could be infinitely many of them, uncountably infinite. But no matter what the configuration of lines, you can associate a maximal function in the following way. I take a a line segment here, and I'm going to consider a probability measure, sigma sub L. So this is just the normalized arc length measure of that line segment. I'm just taking one-dimensional Hausdorff measure, restricting it to that line segment L, and normalizing it to have mass 1. So with respect to this probability measure, I can consider an averaging operator of a function simply by convolving with it. So this is just averaging the function f over this line L at a point x, and then I just take the supremum over all my lines in this line configuration. That gives me a maximal function I'll call m sub L. And the basic object is to try to understand the LP mapping properties of this maximal function for a given line configuration. Okay, so as you can, so there's lots of different types of maximal functions that arise in this way. Yes? All the line segments in your configuration. So you fix a bunch of lines, finite line segments, and you take the supremum over all the lines in that line configuration. So, or infinite or uncountably infinite. For instance, Malavika talked about an uncountable collection of lines. But I'll just begin in this way. So this is, I mean, you can sort of see many examples. You know, the Kakea problem is sort of lurking behind the scenes. And so that suggests that actually there's going to be many line configurations where you'll get no LP estimates for any P. Okay. But there are some, I mean, Malavika was explaining to us, there are some interesting line configurations where you do get LP estimates, and you can get LP estimates for all P bigger than 1. Okay? But I want to begin, let me begin with the general result. So this is the result of my Christ. So it's an old result of his that goes back, I don't know, late 80s, early 90s. And what Mike's result says is that, okay, you might have some nice, interesting configurations of lines so that you get LP boundedness, maybe for all P bigger than 1, but you never get weak type 1-1. That always fails. Okay, so more precisely, what his result says, suppose you start with, say, a finite collection of lines, let's say n of them, with distinct directions. So that's the key word. Okay, they're all pointing. You have n lines pointing in different directions. I don't care how small the angle separation is between these lines. Then you get a bound on the weak type 1-1 operator norm of the corresponding maximal function. Okay, and it blows up with n. Okay, in fact, he proves that this is bounded from below by some absolute constant, only depending on the dimension that you're in, times n. So it's as bad as you can get. Okay, so Mike gave a very nice, clever algorithm that no matter what the line configuration is, this algorithm tells you where to place strategically a bunch of small balls. And then if you look at the sum of the characteristic function of those balls on this maximal function, you get this bound. Okay, so immediately there's a lot of interesting questions. I know this is an old theorem, but there's lots of interesting questions. If you look at Mike's construction, his general construction, it won't produce counterexamples in LP for P bigger than 1, but it will produce failure not only on L1, but for spaces that are slightly smaller, that are locally smaller on the scale of Orlid spaces. And it's an interesting question to figure out exactly which Orlid space that these things fail on. For say, for a general configuration or for some particular one. We'll look at some particular ones. Okay. So that's the first result that I want to keep in mind, this type of counterexample. And now let me move to a particular line configuration. So I want to look at now where all the lines are centered at a given point. Okay, so these are going to be, again, different lengths, different directions, but they're all centered at some point. So I'll call these centered line. Okay, so this is exactly the situation that Malavika was explaining to us. And she did so in a very elegant way and gave us a very nice definitive result. It reminds me of, it's very difficult giving talks after Malavika. I went to Madison once, and Malavika was there, and she she wanted to go to a conference, and she asked me to fill in for her teacher plane geometry class. It was a disaster. I went in there, and soon the students were rebelling, bring back Malavika. Anyway, okay. Anyway, so I'm not going to, so she gave us this a very elegant way of understanding these things. I just want to recall a few things, because I want to highlight a few points about the situation. First of all, as you mentioned, there's the theorem of Nagelstein and Wanger. Okay, so this is actually older than Mike's result. It goes back a decade earlier, mid to late 70s. And it says, suppose you have, now this is just going to be, I'll state this in the plane, 2 dimensions. Got a bunch of lines. So we're going to suppose that these, the directions of these lines lie in a Lacunary set of directions. Okay. So whenever this is the case, so the slopes, for instance, are like 2 to the j. So then you get that the corresponding maximal function is bounded on all LP. Okay. For all p bigger than 1. Okay. So that was a very interesting result. At the time, they introduced some new techniques, very novel techniques that were now they've become standard. But there were Fourier analytic techniques using square functions. And so one started naturally, because they're quite singular maximal functions, one started naturally on L2, getting bounds on L2, and then bootstrapping your way down to getting LP estimates for all p bigger than 1. But there were other techniques at the time. There were more geometric techniques using covering lemmas, but they seemed not to work. They only gave boundedness for p bigger than 2. And there seems to be some obstruction on L2 to get these geometric covering lemma arguments to work below L2. So it's something that I would be interested in asking this question again. Could you push those geometric methods below L2? I think people have tried. I don't know if that has been succeeded yet. And the reason is, now going back to Mike's result, although these guys are bounded on all LP for p bigger than 1, they're not weak type 1, 1. Okay, so I think it's an interesting question to ask what happens near L1 for these guys. And Fourier analytic methods tend to give you LP estimates where the LP bounds are blowing up quite badly as p goes to 1. And more geometric covering lemma type arguments tend to give you more precise information about what's happening near L1. So that's a question. Okay. So as Malavika told us, this has been generalized by Schollin and Sjogren to if your set of lines are lying in a Lacunary set of finite order. Okay, so I won't recall what that is. Malavika explained all this, but you have this now very nice result, more recent result of Michael Bateman. Okay, so Bateman says that more or less, if you have a Lacunary set of finite order, or more precisely, a set of directions that's finitely covered by Lacunary sets of finite order, this is equivalent to the non-existence of a Kakeya set with respect to these set of directions, as Malavika described in her talk, okay? So I won't write that down again, but this is a strong counterexample. When it works, it doesn't only give you LP boundedness for unboundedness in 1p, but for all p, okay? But so that's very strong, but yet it's quite restrictive. I just want to keep this in mind. It only works for centered line configurations. And it's interesting to compare this to Mike's counterexamples, which tends to be restrictive to getting counterexamples near L1, but it's much more general. Okay, so these things are nice to keep in mind as we go along. And of course, Malavika explained this is together with her collaborators, have generalized Bateman's results to higher dimensions in a very nice, definitive way. All right, so now I claim that as you move away from a centered line configuration, you could have the situation where your lines are pointing in directions which are not Lacunary. In fact, the slopes are arithmetic, so they're not even going to be in a set of Lacunary set of finite order. So there exists a Kakeya set, but nevertheless, the maximal function is bounded on some LP. Okay, so this can happen when your configuration, you have a bunch of line segments that are end to end. Okay, so let me draw the picture. Okay, so here's the picture. You've got a bunch of line segments, and they are sort of end to end here. I'll call this a polygonal line configuration. Okay, so the point here is that the union of these lines, as you vary over your line configuration, forms a nice continuous curve, which I'll call capital gamma. Okay, so I want to look at two examples here, okay, and I'm only going to be looking, and I'm only going to be concentrating here in 2 dimensions. Of course, you could ask these questions in higher dimensions, but we know a lot less of what's going on in higher dimensions. So let's just concentrate in 2 dimensions. I'll make one simple observation. You can take this whole configuration and translate it or rotate it without changing the operator norm. So sometimes it's convenient to assume that this continuous curve is emanating from the origin, and you rotate it so that it's given as the graph of some function. So let me make this assumption. I'm going to assume that this curve is the graph of some function, which I call little gamma. Okay, since it's coming from this polygonal line situation, little gamma is piecewise linear. Okay, so for the 2 examples I have in mind, okay, I'm going to assume these are examples where the line segments are actually linear on the classical dyadic intervals from 2 to the j to 2 to the j plus 1. So on such a interval, my little gamma is going to be linear, so it's going to have the form mj plus b. So mj is the slope, and you have some y-intercept. Okay. So all I have to tell you, I'm going to consider 2 examples here. Okay, the first example, let me just remind myself. So the first example, so I just have to tell you really what gamma does on these points 2 to the j, and that'll pin down the curve. So it's just j times 2 to the j. Okay, so you can make a computation. It's very easy. The slopes in this case, m sub j. If you do it, and I did it earlier, you get j plus 2. Okay. Okay, so this is actually a set of lines now, and their slopes are arithmetic. So there exists a Kakeya set for the set of directions. But nevertheless, it turns out is that the corresponding maximal function is bounded on L2. Okay, so we'll come back to that to explain why, all right? But also, it turns out you have some unboundedness results. Okay, now Mike's general construction is not going to give you any unboundedness for LP, but you can take a different lattice that's more adapted to the geometry of this particular example, and you can place your small characteristic, small balls. And in fact, Mike did this. He showed us that in fact for this example, this explicit example, you're not going to get any LP boundedness in a range, and the range he got was up to 4/3. Okay, so you can actually tweak Mike's argument a little bit and improve this slightly, and you can get unboundedness in the range up to 3/2. So this was an observation of Andreas Zieger, Steve Wanger, and Sarah Ziesler, myself. And it's an interesting question. Yet another question of what happens between 3/2 and 2. We don't know for this particular example. Okay, so that's the first example. I want to look at the second example, okay, is when you take gamma of 2 to the j to be 2 to the 2j. So this is just taking the classical parabola tt squared and polygonalizing it at the points t equals 2 to the j. Okay, you make a computation. You see that the slopes in this case is 3 times 2 to the j. So these are geometric. Okay, so you can't apply necessarily the theorem of Nagelstein and Wanger to this because these are not centered lines, but you can modify their argument, and you can show that the corresponding maximal function is bounded on all LP. Okay, so this is actually a result that's contained in the famous paper of 8. Okay, so usually people refer to this as CCC dot dot dot. It's a little bit of, you know, there are three authors that their names begin with letter C. It's a little bit unfortunate for those people that have names at the end of the alphabet. So let me try to remember. I know that that's clearly Mike. Chris got to be one of these things. I think it's Anthony Cordoba, Hasse Carlson. Then there's Ruby de Frantia, Javi Doente-Cachea, Jim Vance, Steve Wanger, David Weinberg. Okay, so that's it. Okay, so this is Steve has a very funny story. Steve Wanger, he was sitting in the airport, I think it was Chicago O'Hare, waiting for a flight, maybe going to a conference, and he was chatting with a physicist, a particle physicist, going to some other conference. And they were talking about collaborations, and the particle physicist said to him, you know, I'm rather famous because I'm co-author of a paper in my area with the least number of co-authors, 12. Steve said, well, anyway, okay. So we have this boundedness result. Now, you could ask, of course, Mike's result tells us it's unbounded on L2. Sorry, it's bounded on all LP, but Mike's result says it's not weak type 1,1, okay, for this example. So this is, but you could ask, what does Mike's argument give you? And so if you look at Mike's argument, you get unboundedness on a scale of Euler spaces. And if you do the computation, you get some L log to a certain power L. It does not map into weak L1 for any sigma up to a half. Now, I have no idea whether L square root log L is appropriate for this operator. But L square root log L is an interesting space, one of my favorite spaces. It does appear quite often. It happens to be the endpoint space for classical Marcinkiewicz multipliers on the real line. You get boundedness on this space, and that's no better. Anyway, okay. So these are lots of questions here. Now, what I want to do is I want to so now I'm going to have to do the hard bit. Start rubbing off. Okay, this is the unpleasant part. Let's see. I know that Hilbert gave me a tutorial on this. Let's see if I can do it. Okay. All right, so I do this, right? Go all the way across, down. You did this much better, Hilbert, somehow. Okay, I'll do it like that. Okay. We'll try it like that first. Yeah. Hmm? You want me to try it? Okay, let me try it. There's one extra feature to this tutorial. You got to do this now. I don't know if it's doing anything. Anyway, okay. All right, so what I want to do is I want to take these examples these two examples, okay. These two examples here, now I can think of these as averaging over these polygonal line segments, but you can also think of this as averaging along this curve gamma. It's quite easy to see that these examples, for these two examples, this maximal function is actually pointwise equivalent to averaging your function along the continuous curve gamma of t, say from 0 to h, divide by h, and take the supremum of h positive. And what we arrive at, this is called I got to use a different letter, let me script m. We arrive at what's called the maximal function along the curve gamma. Okay, so this is, so Eli in his talk and also in Polam, this is part of, these are very singular maximal functions. I can start to think of this more generally for any continuous curve, not necessarily arising from a polygonal line configuration. These are examples of singular Radon transforms, singular maximal Radon transforms that's been talked about in a few places. And these things I think for this particular example, Eli told us where some other maximal Radon transforms arise from. I think these were given, am I right? I think it's in your ICM address that you presented this to the world in 1970. And you suggested that, so these were related, for instance, to the problem of pointwise convergence, almost everywhere convergence for Poisson integrals on symmetric spaces. But a lot of these singular Radon transforms come from a variety of different problems. Okay, so this is the maximal function. And now I want to just think of it as a continuous curve. And I'm going to sort of shift now to things, maximal functions along curves. Now I'm going to just concentrate the attention here to 2 dimensions. Again, you can think about this in higher dimensions, but we know a lot less. Okay, and I'm going to make one geometric assumption, is that I'm going to assume also that this is convex. Okay, and I'm going to tell you why I'm going to make this assumption. Even with this assumption, there are lots of examples of convex curves, even smooth ones. So where the LP boundedness of these operators are unbounded on all LP. But we've already seen examples, like along TT squared. We've already seen examples where this is bounded on all LP. Okay. Now, why do I make this convexity assumption? It actually, there's a good reason for this, because it does simplify the analysis in the following way. If I go back, now I'm thinking about a general curve. I can think about, which is averaging along the curve, but again, I could go back to only average along dyadic pieces, say from H to 2H. Okay, so so let's say this is just averaging between H and 2H, and I can just, in fact, restrict myself to H dyadic if I like. And now one of the key things when you look at these singular maximal operators, how you can get your hands on it, using the most successful technique is using Fourier analytic technique, square functions. And so there's a way that if you can detect that these underlying averages defined in your maximal function has some smoothing on the scale of Sobolev spaces or LP spaces, if there's some smoothing, then you can prove positive results, LP estimates for this maximal function. So this goes back to work of Eli and all of his collaborators. So let's look. One way to detect smoothing with respect to a singular measure is to understand the decay of the Fourier transform. So if I compute the Fourier transform, this is some measure on the plane. So it's an oscillatory integral, say from H to 2H, of e to the I ct plus e to gamma of t. Okay, and I want to understand how this behaves for large c and eta. So you have to understand where this phase becomes stationary. Okay, and notice that so in other words, the critical points of this stage are very simple. Okay, there's at most one critical point. So that's if it's strictly convex, but if it's but in general it's just a single interval of critical points for this phase if gamma is convex. Okay, so the convexity assumption tells you that the geometry of the critical points of the phase is very, very simple. It's either a single point or an interval. Okay, so that's what, so I'm going to make this underlying assumption, and here the goal I'm going to propose, and I don't know how feasible this is, but is to try to find a nice necessary and sufficient condition on the curve gamma. So this just a curve which is convex that guarantees that the corresponding maximal function is bounded on L2. Okay, so I don't know how feasible this is. Certainly Steve Wanger would like to, he would love to see this goal realized in some way. I mean, you might ask why L2 doesn't necessarily mean it's not such a natural space necessarily for maximal functions. Of course, the techniques, Fourier analytic techniques using square functions is natural from that point of view, but we've already seen an obstruction on L2 for certain methods to work. You could also think about Mike's counterexamples, and I don't, they tend not to work beyond L2. I don't think that there's been an example. I don't know, for instance, of a nice convex curve in the plane where you get unboundedness for a range of p bigger than 2, and then it becomes bounded. I don't know an example, for instance. Okay? So that might, there's some possible obstruction, but anyway. So I'm going to write this as a goal. It is true. Let me just pause for a second. Okay? And can I pause? Oh, am I out of time already? When did we start? An hour ago? Oh, okay. Oh, Jesus. All right. Okay, we'll end early. Okay. Okay. I shouldn't have drank that coffee. There are other situations. Here's a situation that's related to these type of maximal functions. Instead of averaging, look at maximal functions where you average a long gamma, I'm going to average over gamma. Suppose I take a convex curve, a compact convex curve in the plane, say the origin is somewhere in the middle, and I'm now going to look at an average over it, say with respect to arc length measured, d sigma, which I'll assume to be normalized at mass 1. So I'm going to look at convolution over this, so this averaging operator. And then I'm going to consider dilates of this, but I'm only going to consider Lacunary dilates and take the supremum over all Lacunary radii, and that gives me a maximal function. I'll call that n sub gamma. So it's a Lacunary maximal function. So for instance, if you consider all radii and you just have a circle, that's the famous circular maximal function. But in this case, when you take Lacunary dilates, it's well known and quite easy to prove that if this curve is finite type, that is, there's no point on the curve that's the curvature vanishes to infinite order, then you get LP boundedness for all p bigger than 1 for such a thing. And it's a big unsolved problem, even for the circle, whether this Lacunary maximal function is weak type 1,1. We don't know. So that's another interesting problem. Now what I'm going to look at is a condition on this curve. I'm going to now be allowing the curvature to vanish to infinite order, but I'm only going to try to characterize the L2 boundedness. So here's a condition that does that. So what I'm going to do is I take a point on this curve, P. I'm going to now define a little cap around it. I'm going to take the tangent line here, go in a normal direction by amount delta, look at the parallel line, and this cuts off a cap. Oh, what did Malabika use? You had some high technology here. So there is a colored cap. I'll call that C, centered at P, radius delta. So if I take the arc length measure of this guy here, and I look at its, and the condition is asking it to be square summable with respect to the invariant measured d delta over delta, I integrate for small delta, say, and take the supremum over all the points in the curve, and I'm going to ask when this is finite. So I'll call this condition C. Okay, so that you can check. Ooh, I have to do some more rubbing off. So you can check that there are certain, that allows for flat examples, but not all flat examples. Okay, so let me try this. Ooh, sorry. That worked a little better, I guess. Now you do this. Oh, yeah, okay. How was that, Herbert? Good, okay. I also had a job with Ben as a window cleaner, but I was fired, actually, halfway through the summer. Anyway. So it's an observation. So here's a proposition. This is an observation of Andreas Ziegler and myself that this completely characterized L2 boundedness. So that this, what did I call this? N sub gamma is bounded on L2 if and only if this condition, maybe I should call this C2. There's an LP analog if this holds. Okay. So you can characterize it perfectly in this way. We don't know what happens in LP for P different than 2. Another nice question. I replace 2 with P, and that becomes a necessary condition, but we don't know if it's sufficient. Doesn't seem to us to be completely straightforward. Another.
Constants in the LP bounded operator are comparable in some way to the C2?
Yes. Square root, thanks. Yes. Okay, so let me, okay, so that's just an observation. That's another question that we don't know how to do. Now let me let me go back to these curves, this maximum function along convex curves, okay, and tell you a little bit of a difference between, we introduced them by these polygonal line configurations and compared them with what happens when everything is centered. So a difference with the centered line configuration that we have for these operators, here's a difference, is that there is a natural singular integral operator associated to this curve called the Hilbert transform along a curve. So we're just convolving along the curve, but we're putting a classical Hilbert transform singularity dt over t. You have to define this in some principal value sense, okay? So this is, these singular Radon transforms actually arose from a different problem. It was trying to generalize Calderon-Zygmunt theory, the method of rotations, to other dilation groups. So here, I have to tell you, because so this maximal function is only defined for t positive, I have to tell you what's going on for t negative. So I have this nice convex curve here. And so how I define it's going to tell me what the cancellation is. And it's important how I do it. And I'm only going to do it in either one way, in an odd way, so I'll call that odd, or in an even way, and I'll call that even. And I'll look at the corresponding odd or even Hilbert transform. Okay, so the idea is that the theory for the maximal function traditionally has evolved at the same time as understanding this convolution operator. So this L2 is definitely a natural space to study this guy. It's just a multiplier. You just have to bound an oscillatory integral. Okay? And so there are nice results. Every time we get a result for the singular integral, we can try to prove the same result for the maximal function. So that's the basic theme. So you'll start to appreciate the singular integrals coming into it. And I'll try to make a connection a little bit more. So here's some theorems. So let me be quickly, sorry. So these are a lot of theorems with a lot of names attached to it. So I hope I can get this right. Let's look at the even one. Okay, and you can characterize L2 boundedness. That's just a multiplier. And what you get is this is equivalent to looking at the slope of the tangent line and requiring that that doubles, that there's a constant bigger than 1, such that if I look at the slope over a dyadic interval, so I go from t to lambda t, I require the slope has to at least double. So that's called gamma prime doubling. So that characterizes the L2 boundedness for this singular integral operator. Okay, and then you could ask if it's true whether you get LP boundedness for the maximal for L2 boundedness. In fact, if the other observation, if gamma prime doubles in this way, then in fact that's a sufficient condition to guarantee that this is bounded on L2. And what's more is you can even do better. This gives the characterization for all LP. Okay, so this was actually the content, the LP result, in this paper of 8. But the L2 result actually came earlier for the Hilbert transform in a paper of Nagel, Vance, who was it? Nagel, Vance, Wanger, and Weinberg. Okay, for the L2 result. So that's the generalization. That was, of course, generalizes this TT squared, where we had this polygonalized TT squared. Of course, we were doubling the slope each time we moved from one dyadic interval to the next. So that is subsumed in this result here. Okay, so this is a sufficient condition that guarantees boundedness for the maximal function. Now I want to look at a picture. Okay, so and now I want to move to the odd extension. So here at a point t, I look at this tangent line. So the slope of this tangent line, of course, is just given by the derivative of this function at t. But now I want to look at its y-intercept. And I'll call this h of t. So that's another functional associated to this curve. And the result here, theorem 2, simply says that, I should be a little more quick here, that you can get characterization. I don't don't need this to be perfect, I don't think. Okay, not perfect. Okay, so here's theorem 2 that says that you have the odd extension is bounded on L2 if and only if this h, the y-intercept, which is increasing because of convexity, is doubling. And then you could ask whether or not this is a sufficient condition for the maximal function, and it is. So h doubling implies the maximal function is bounded on L2. Okay, so this is strictly an L2 result. If you go back to the example, that example 2, oh no, it was example 1. If you remember, we took as our polygonal lines j times 2 to the j at the point t equals 2 to the j, and that gave me these slopes that were arithmetic. Okay, but if you do a little further computation, you can compute the y-intercept for this example, and you get that you get 2 to the j. So in this example, it's the h, the values of h are doubling over a dyadic interval. That's precisely this h doubling. That's why in this example I claimed that the maximal function was bounded on L2. So this comes from work, again, of Nagel, Vance, Wenger, and Weinberg. These two results, I think, I hope. Okay? So this is, it's even more interesting. There's no LP theory for this. For this example here, the associated Hilbert transform, the odd extension, this is actually bounded on L2 according to this, but you don't get any other boundedness. And that was an observation in a paper of Mike Chris and Tony Carberry. Did I write? And who else, Mike? Help me out here. You, Carberry, Vance, Wenger, and Watson. Okay. So remember, we had boundedness on L2 for the maximal function, according to this result, and we had unboundedness for that maximal function in some range of LP. And we didn't know between 3/2 and 2, but here for the singular integral, you have perfect a decision on this part. Okay. So I just want to finish now. I now want to, so that's basically where the theory has stopped for a while, because more or less that is where the, where are my notes? That has 5, where's page 6? Oh yeah, here's page 6, but okay. So that's basically where it has stopped, because that is as much as what the singular integrals of these two singular integrals has given us. Okay, we've squeezed as much out of it for the maximal function. So whenever we could say something good, we should note, I should have made an important observation, that these two conditions, one is stronger than the other. Gamma prime doubling actually always implies that h is doubling. So this is the weaker of the conditions, this h doubling. This gives us the strongest result for the maximal function on L2 that we know. And basically, that's how things have stopped, because this is what we can learn from the singular integral. So I want to propose a new perspective. I just want to end with talking about some more recent work. This is joint work with Mike Christ and Steve Wenger and Jim Vance. And our perspective is to try to consider now yet more singular integrals, okay? More singular integrals that are associated to this curve, which may be a little bit more closely associated to this maximal function. In fact, I had a very interesting conversation with Fedya Nazarov about this and explaining these things, and he got very, very excited. And as Ben will vouch, and I'm sure you will vouch as well, when Fedya gets very excited, you don't know what's going to happen. But he started to make connections with this problem and these problems about singular integrals, L2 boundedness, and rectifiability. I don't understand these. Maybe they were just analogies, but it was hard for me to understand exactly what he was on about. So what we're going to do is introduce So let me make one comment before I do that. So how do the proofs of all of these go? Okay, so these are very singular maximal functions. So they're going to go by square function technique. So basically what we're going to do is we're going to compare these singular averages. So I've got this convex curve, say between h and 2h. And I have this very singular average. I'm going to compare it to a more smoother average. And the comparison is going to be controlled by a square function. And so this square function is going to look like a singular integral, one of these singular integrals here. And the idea is then to use the methods we know for singular integrals to prove this. Now, I don't really need a Calderon-Zygmunt theory attached to these smoother averages because I'm only doing L2. So the balls here, for when gamma prime is doubling, so this theorem 1, so you could take just these balls here. I can just take these balls and compare it with just averaging over this very thick thing, okay? And the comparison, I take the difference and I get a square function, and the singular, and I can mimic what happens for the singular integral and get the estimate. So that's how you can prove, for instance, theorem 1. For theorem 2, okay, you need to be a little bit more subtle. So I have this average, singular average along this curve. What I do is I take this tangent line, and then I go stop at 2 to the h, go up to the curve, and I look at this parallelogram. So this is the family of balls that I should be looking at. And then when you make the comparison, I have a square function to look at. And then I try to see that if this theorem, if the proof of this theorem goes through for this maximal function. And that's more or less what happens. Okay. So now I want to introduce, so this is for h doubling. Okay, now I just want to introduce the only further progress is made is by looking at yet another singular integral operator, which is called the singular integral of fractional order of integration along the curve. So I'll call this t, and there's a real parameter sigma, and here I'm going to be integrating along this curve. But I'm going to, instead of integrating 1 over t symmetrically, the cancellation is going to be encoded in a logarithmic oscillation given by t to the I sigma. Here, sigma is some non-zero real parameter. Okay, that's called the integration log. So that's, again, a convolution operator. To understand on L2, we just have to understand the multiplier, which is a little bit more subtle. We haven't characterized when this is bound on L2. But this mimics the maximal function. So for instance, I'll just say in words, I'm running out of time. If your curve had a long piece of line, okay, in it, and if you looked at these other two, either the odd or even extension, you look at the multiplier and the Fourier variable was orthogonal to that straight line, then you kill the oscillation and you just pick up the logarithmic measure of this interval, which could be large if your line segment is large. But if you do the same thing for this guy, if this guy contained a long piece of line segment, you know the maximal function along a straight line segment is completely controlled. It's just the Hardy-Littlewood maximal function in a given direction. And this logarithmic oscillation is strong enough to give you uniform boundedness of the multiplier along a long straight line. Okay, so here's the improvement, and I'll end with this. It turns out that we can weaken this h doubling in the following way. Okay, so here's the condition. I'll write it as C. So I'm going to look at a long strip, so 2 places, A and B, where this h has not doubled. Okay, so if h is doubling, that's just a dyadic interval. Okay, B over A is control. So but let's suppose this could be a very long space. And when this happens, I'm going to assume that most of the curvature is concentrated near the left endpoint, A. So the picture is I have this long stretch here from A to B. And most of the curvature I'm going to assume is concentrated near A. And I'll express this in the following way, that if I look at the weight, the second derivative, the curvature with t, and I integrate from A to B, I'm going to assume that I can pull out t at the upper end point. Okay, so that's a way of, so that's the condition I'm going to suppose, and of course that's more, that of course is implied by H doubling. When H doubles, then the ratio of B over A is controlled. I can always pull out T at the upper end point. Okay. So this is a weaker condition, and the proposition is that this the singular integral under this condition is bounded on L2 if C holds. Okay, so that's and here the theorem is that if C holds, then the maximal function is bounded on L2. Okay. Okay. So here, just to finish, what I'm going to, the balls, where are the new balls? Where are the new balls? So that's the theorem. Sorry. So the new balls are this, that if we're now in a very long stretch, of course I'm going to use all of these balls. I'm going to, first of all, think about what happens when the derivative doubles, and then look at what happens when between where H doubles, and use these balls to control that. But now suppose I'm in a very long stretch where H is not doubled yet. So I have that this condition holds. So the balls that I want to use here in this part of the operator, so this could be a straight line. So I'm going to pin it down at this upper end point and consider going from, say, H to 2H. I'm going to consider this long stretch and then go up and just consider this parallelogram here. Now notice that these balls completely degenerate to a line if it's a straight line. Okay, so when I make this comparison, okay, I'm looking at the maximal function along a straight line, and I'm just going to compare it to the maximal function along the straight line. That part, when the maximal function along a straight line, I know how to control just by the Hardy-Littlewood maximal function in that direction. But in general, these are the appropriate balls that allow us to control the part of the curve where H is not quite doubled. Anyway, so this doesn't give us the goal. We can extend this in various ways to get stronger results, but still we are somewhat far away from the goal. But who knows, maybe introducing more singular integrals into the picture, we could get closer and closer. So thank you. Yes. Well, these do, yes. Okay, because they don't come from a space of homogeneous type, but you can, for instance, you have this property that if you look at 8 of them around, that their measures are comparable. So they don't satisfy this dilation property, but there's a cover in them. So for instance, these guys here, the corresponding averages are all weak type 1-1, for instance. I don't know, but that sort of reminds me of the problem along vector fields. Averages along so your lines are changing according to a vector field. So that's one of these singular Radon transforms. We have, I don't know if there's the application you have in mind, but there are positive results. For instance, in the work that Eli mentioned of Christnagel, Stein, and Wenger, as long as the vector for the integral curves of the vector field, the curvature doesn't vanish to infinite order, then you can get positive estimates. But in that example, this is a famous problem. I think there's the maximal function goes back to Zygmunt, an aspect of it. And that is, you shouldn't assume any curvature conditions. So that's this problem that we don't know. It's something that people, I think, have thought about. But the function, instead of on LP, you want some other spaces. You could ask these questions, and the only way I can answer that is that I know you can get it by interpolation, some estimates on these things, but more subtle estimates I don't think are known for these type of operators. Yes. It's not that related. No, I just started. It was just a question someone asked me last week, which they were interested in. That came from this theory, and they told me a very explicit question, which I solved for them, and it just reminded me of all these, and I was something to talk about. Yeah. Oh, yeah, of course. This is silly, right? Yes, sorry, thank you. Definitely A, right? You can always pull up, yes.
But suppose they're given an X, like a radius of a ball. Right?
Yeah.
How do you determine which A or B you use in order to do the construction to construct this ball?
Well, first what you're going to do is the idea in this case is to look at, you have your curve, and then you want to look at the places where the slopes have doubled. Okay, so you do a partition of the curve where the slopes have doubled. And then you can use a general argument that says that if you can control the averages between these points, I can put those together. So that's sort of a modification of the Nagelstein-Wenger theory that allows us to do that. Then you could ask further, I want to now go and decompose that part into places where H is doubled. So I do a further partition for H has doubled. Okay, those could be still long stretches. And then you want to be able to prove that if you can uniformly control the averages between where H is doubled, you want to put those together. And that more or less comes from this sort of theory here, where H is doubled. You have to modify that in order to get to reduce it. Now I'm in a place where I'm looking at averages where between 2 points along a curve where H is doubled. So this condition now automatically holds. This is my
No more questions. Thank you.
Okay.